Let us now see how to determine magnetic field due to straight current carrying wire at given point. So we will have to consider a straight wire which is carrying some current I. We will consider some point outside it, and then we will see how to determine magnetic field. So let us first consider the wire. Say this is a wire and it is carrying some current I. Let the current be I. Okay, and what I want to do, I want to determine magnetic field. Where, say, I want to determine magnetic field at this point, which is P. But where is P? So, I would say that point P is at distance y from O point. Let O be foot of perpendicular from P on the wire. So, where is point P? It is at y distance from perpendicular distance y from the current carrying wire. Okay, and I want to find out magnetic field. So, what the Biot law says, it says that you'll have to have ideal cross R. Okay, so what is ideal? First of all, I should have current element chosen, and then with respect to the current element, I should have position vector of point P. So let me consider current element here. Here means where? So I would say that I am considering a current element IDL at distance x from foot of perpendicular. Okay, and where is point P? So the point P is considered at say distance r, or say position vector r with respect to IDL. Okay, so this is the consideration. Let the angle be theta. Okay, and if the end points of the wire are A and B, then let the angle subtended at point P be theta 1, which is in clockwise direction, and B, say it is theta 2, okay, which is in anti-clockwise manner. Sorry, this is theta 2. So this is the situation, and we want to determine magnetic field at point P. So now, when we apply Biot law, we'll see that first of all we'll need to determine value of sorry, value of IDL. So here my IDL is, can I say it is IDX, because current is in X direction, so IDX I cap, right? And R, what is the position vector R? So I would say it is minus X I cap plus Y J cap. Why minus X I cap? Now look at the R vector. R vector is going like this, isn't it? So if you look at the X component and Y component, Y is going in positive Y direction, but X is going in negative X direction. So when you write the components of R, it should be minus Xi cap and uh, plus Y J cap. Okay. So with this consideration, uh, we have now IDL and R both. So what is IDL cross R? So if I take IDL cross R, I have IDX I cap cross minus Xi cap plus YJ cap. So what is I cross I, it will be 0. And what is I cross j? It will be k cap. So ultimately what do we have? So ultimately we have IDL cross R as I y dx k cap. I cross j is k cap. Okay. And now I can substitute this ideal cross R in the formula. Now what was the formula? Formula says that magnetic field can be given as mu 0 by 4 pi IDL cross R by R cube. Okay. One more thing here. As we can see from the figure, see, if you look at the geometry, here is R, here is Y, here is X. So I can say that R square is X square plus Y square, or R is X square plus Y square raised to 1 by 2 or square root. So what is R cube? R cube is X square plus Y square raised to 3 by 2. Okay. So I'll substitute all these values in the formula, and then we have mu 0 I by 4 pi, and look at the cross product I y dx k cap. I is already considered, so y dx k cap, and in denominator I will write x square plus y square raised to 3 by 2. So this is the magnetic field. Is it total magnetic field at point P? No, this is the magnetic field at point P only due to this current element IDL. Okay, so we'll have to integrate over total length. But then we have one easier option. If we can take help of trigonometry, the task would be slightly easier. So let us consider trigo, and that will make the integration part a bit easier. So again, look at the figure and see here. Can I say tan theta? Tan theta is x by y. Okay. So what is x is equal to? X is equal to y tan theta. And then if you take dx by d theta, if you differentiate this with respect to theta, you will get y sec square theta. So dx becomes y sec square theta d theta. So we have dx value, we have x value, and the two can be substituted in our formula. Okay, and though you may not be convinced at this point, but it will definitely make our task smoother. So now after substitution, the dB would look something like this: mu 0 I by 4 pi. Okay, y, as it is, y is constant. See, go to the formula, look at the formula, y is constant. So we don't bother much about y. And instead of dx, now I'll take y sec square theta d theta upon, instead of x, now I'll take y square tan square theta plus y square raised to 3 by 2, and all these things are in positive x direction, so k cap. Simplify further, so what you'll have, mu 0 I by 4 pi y square sec square theta upon y cube tan square theta plus 1 raised to 3 by 2. How come cube? Because if you take y square common, if you take y square common, it will have power of 3 by 2. and simplifying this, we will have y cube. Okay, so that's how we get y cube. And now still we can simplify further. This tan square theta plus 1 will give you sec square theta. So 1 plus tan square theta, 1 plus tan square theta is sec square theta. Okay, and so you have sec square theta raised to 3 by 2. What is that? It is sec cube theta. And of course y square upon y cube, we can definitely simplify. So dB becomes mu 0 I by 4 pi sec square theta y sec cube theta. Okay, d theta, I forgot d theta here, and k cap. So sec square theta upon sec cube theta, what it will get us? It will get us 1 by sec theta, and what is 1 by sec theta? It is cos theta. So this dB is now mu 0 I by 4 pi y d theta by sec theta k cap, or else I can write it as mu 0 I by 4 pi y cos theta d theta. Okay, and now if you try to find out b, you just have to integrate cos theta, and that is why it is easy if you take help of trigonometry. Okay, so now we'll find out total magnetic field B, which can be given as integration dB. Okay, so I will take mu 0 I by 4 pi y outside, and I'll take cos theta d theta k cap. What should be the limit of integration? So we know that one side of the wire is subtending angle theta 1, whereas the other side is having theta 2, but the theta 1 is in anti-clockwise manner, whereas theta 2 is in, sorry, theta 1 is in clockwise manner, theta 2 is in anti-clockwise manner. So theta 1 is considered as minus theta 1, theta 2 is considered as plus theta 2, and then my limits of integration will be minus theta 1 to plus theta 2. What is the integration of cos theta? So integration of cos theta is sine theta, and hence you will have mu 0 I by 4 pi y sine theta minus theta 1 to plus theta 2, and then you will have b a cap, I forgot here. So mu 0 I by 4 pi y sine theta 2, upper limit minus lower limit sine of minus theta 1, but in case of sine, we can write this equation as mu 0 I by 4 pi y sine theta 2 plus sine theta 1, possible only if it is function of sine, not for cos function. And then this is the formula for magnetic field due to straight wire carrying current I. Okay, using Biot law. Now there is one point here we should note down, that sometimes you may be given angle subtended at endpoint. Suppose angle here at say A point is alpha 1 and angle at B point is alpha 2. So if you don't have theta 1 theta 2 given, and if alphas are given, then this formula can be written as B as mu 0 I by 4 pi y cos alpha 1 plus cos alpha 2 k cap. Okay, so both these are possible form. Whichever formula you are comfortable with, you can use. This formula, when you are given angle at the point of interest subtended by ends of the wire, and this formula are when the angles at end points of the wire are available. Okay, so that was the formula, and then we will see special cases. So in the next video we will see special cases. This is all for now. Thank you.